Welcome to today's problem walkthrough. We'll be exploring the problem number 374, guess number higher or lower. In this problem, you'll learn how to efficiently identify a hidden number using the provided guess API. We'll evaluate different approaches and complexities to solve this challenge step by step. Let's dive in. In this problem, we are playing a guessing game called Guess Number Higher or Lower. The idea is simple. You need to guess a number between 1 and n, where n is the upper limit provided in the input. The actual number to guess is chosen by a system API, and you don't know what it is. To help you narrow down your guesses, the system provides a predefined function called guess, int number. When you make a guess, this function compares your guess number to the secret number and returns one of three values. It returns -1 if the secret number is lower than your guess, 1 if the secret number is higher, and 0 if your guess is correct. Your goal is to implement the function guessNumber, int n, which uses the guess API to identify the secret number and return it. This is the essence of the problem and sets the stage for the examples we'll explore next. Here's the first example to help clarify how the problem works. Suppose n is 10, meaning the secret number is somewhere between 1 and 10, inclusive. In this case, the secret number is 6. Let's walk through the process. First, you might guess the number 5. The guess function would return 1, indicating that the secret number is higher than 5. Next, you guess 7, and the guess function returns -1, meaning the secret number is lower than 7. Finally, you guess 6, and the guess function returns 0, indicating that you've guessed the correct number. So, the function guessNumber would return 6 as the output. This example demonstrates how the feedback from the guess API allows you to zero in on the correct number step by step. Now, let's consider a simpler scenario where n is 1. Here, the range of numbers to guess from is just 1, and the secret number is also 1. Since there's only one possible number, the process is straightforward. You guess the number 1, and the guess function immediately returns 0, confirming that your guess is correct. The function guessNumber would then return 1 as the output. This example highlights that the function must handle the smallest possible input gracefully, ensuring that it works correctly even when the range contains only a single number. In this third example, the range of numbers to guess from is slightly larger, with n set to 2. The secret number in this case is 2. Let's walk through the steps. First, you might guess the number 1. The guess function would return 1, indicating that the secret number is higher than 1. Next, you guess the number 2, and the guess function returns 0, confirming that this is the correct number. The function guessNumber would return 2 as the output. This example demonstrates how the problem works when the range is small but contains multiple possible numbers, emphasizing the need to use the feedback from the guess API effectively. There are a few important edge cases to consider when solving this problem. First, when n equals 1, the range contains only one number, so the function must handle this scenario correctly by immediately identifying the number as the secret number. At the other extreme, when n is very large, such as 2 times 10 to the power of 31, the function must be efficient enough to handle the input without exceeding time limits. Another key consideration is when the secret number is at one of the boundaries, such as 1 or n. In such cases, the function should identify the number with minimal guesses. To achieve this, the problem is best approached using a binary search strategy, which ensures that the number of calls to the guess API is minimized. These constraints and edge cases highlight the need for an efficient and robust implementation. To approach this problem, we start by considering two potential strategies, a brute force approach and an optimized binary search method. In the brute force approach, the idea is simple. We sequentially guess numbers starting from 1 up to n, using the guess API to check if the guess number is correct. While this method is straightforward, it's highly inefficient because it doesn't leverage any strategy to reduce the range of possible answers. The time complexity here is O(n), as we may need to guess every number up to n in the worst case, and the space complexity is O(1), since no additional data structures are used. However, this approach quickly becomes impractical as n grows, especially for large values like 10 to the power of 9, making it unsuitable for this problem. On the other hand, the binary search approach is much more efficient. Here, we start with a search range of 1, n, and repeatedly narrow this range. By calculating the midpoint and calling the guess API with that value, we determine whether the target is lower, higher, or equal to the midpoint. Based on the result, we adjust the range, either discarding the upper half or the lower half. This process continues until the target is found. The key strength of binary search lies in its efficiency. Each step halves the search space, resulting in a time complexity of O log n. Like brute force, its space complexity is O(1), but it's significantly faster, even for very large values of n, and has no notable drawbacks. This makes it the optimal approach for solving this problem. Binary search is the clear choice for this problem because it fully utilizes the information provided by the guess API to systematically eliminate half of the search space at each step. This efficiency is particularly evident for large values of n. For instance, if n equals 10 to the power of 9, binary search would require only about 30 iterations to find the target, compared to up to a billion steps in the brute force approach. When we compare the two strategies, the brute force method is straightforward but impractical due to its O(n) time complexity, which makes it infeasible for larger input sizes. In contrast, binary search operates with an O log n time complexity, making it highly efficient and scalable. Both approaches use constant space, so there's no trade-off in terms of memory usage, but binary search does require more logical reasoning to implement. Despite this, it remains simple and easy to code. Ultimately, binary search stands out as the best solution. It's efficient, scalable, and leverages the feedback from the guess API to minimize the number of guesses. No other approach strikes the same balance of speed and simplicity, making it the ideal strategy for this problem. To solve the guess number higher or lower problem, our task is to efficiently find an unknown number within a range from 1 to n. We achieve this using a predefined guess API, which provides feedback based on our input. The API will return -1 if the guess is too high, 1 if it's too low, and 0 if the guess is correct. The challenge here is to minimize the number of calls to this API while guaranteeing the correct result. If we were to test numbers sequentially, it would take n time in the worst case, which is impractical for large values of n. Instead, we can leverage the power of binary search. Binary search is an optimal approach because it systematically reduces the search space by half in each step, making it logarithmic in complexity. To implement this, we start by defining the range with 2 pointers, low set to 1 and high set to n. Then, we repeatedly compute the midpoint of the current range to focus our search on the most probable section. The midpoint computation, mid equals low plus high, //2, is the key to narrowing down the search efficiently. At each iteration, we use the guess API to evaluate the midpoint. If guess mid returns 0, it means we found the target number, and we can return the midpoint as the result. If the API returns -1, that means the target is smaller than the midpoint, so we adjust our search space by setting high equals mid 1. On the other hand, if guess mid returns 1, the target is larger than the midpoint, so we move the lower boundary up by setting low equals mid plus 1. This process continues until the range is reduced to a single number, at which point the loop terminates. Because the number is guaranteed to exist within the range, there's no need for additional checks to handle missing values. The beauty of this approach is its efficiency. By having the search space at each step, the number of guesses grows logarithmically with the size of the range. This makes binary search an ideal solution for problems like this, where feedback allows us to eliminate irrelevant portions of the search space systematically. In the final stages of the algorithm, if the range has been reduced to a single number, meaning low equals high, the algorithm will correctly identify the target without any further iterations. The entire process is supported by 2 simple pointers, low and high, which define the current search space, and a midpoint calculation that determines where to look next. Importantly, no additional data structures are required, as everything is handled through direct computation and feedback from the guess API. When we analyze the complexity of this solution, the time complexity is O log n, because the search space is halved at each step, and the space complexity is O(1), since we only use a few variables. The Python implementation of the binary search algorithm is both concise and efficient. Here, we initialize low and high to define the range, and within the loop, we compute the midpoint and query the guess API. Depending on the feedback, we adjust the search space until the correct number is identified. This implementation guarantees optimal performance while maintaining simplicity and clarity. This solution uses a binary search approach to efficiently determine the correct number by minimizing the number of calls to the guess API. The function guessNumber begins by initializing two pointers, left, set to 1, and right, set to n, which define the boundaries of the search range. The binary search is implemented within a while loop that continues as long as left is less than or equal to right. Inside the loop, the midpoint of the current range is calculated using mid equals left plus, right left, //2. This calculation avoids potential overflow issues compared to left plus right, //2. The midpoint value is then passed to the guess API, which returns one of three possible results. 1. If the result is 0, the correct number has been identified, and the function immediately returns mid. 2. If the result is -1, it indicates that the guess number is too high. The search range is adjusted by setting right equals mid 1 to exclude the upper half of the range. 3. If the result is 1, it means the guess number is too low. The search range is adjusted by setting left equals mid plus 1 to exclude the lower half of the range. The loop continues narrowing down the range until the correct number is found. In the edge case where the loop exits without finding a number, which theoretically should not happen given valid inputs, the function returns -1 as a fallback. This implementation efficiently identifies the correct number in O log n time, making it well suited for large input sizes up to the maximum constraint, n equals 2 to the power of 31. The binary search approach ensures minimal calls to the guess API, adhering to the problem's requirements for optimal performance. This is the Java implementation of the LeetCode problem number 374, guess number higher or lower. The code uses binary search to efficiently determine the correct number by repeatedly adjusting the search range based on the guess method, which indicates whether the current guess is too high, too low, or correct. Key differences from Python include Java's strict type declarations and syntax. The solution inherits from the guessGame class, where the guess method is predefined. To solve the problem, we use a binary search approach to efficiently narrow down the possible range of the target number. In the first example, the target is 6, and the input range is from 1 to 10. We start by initializing two pointers, left at 1 and right at 10. The first step is to calculate the middle point using the formula mid equals left plus, right left, //2. This ensures we avoid overflow in case of large numbers. For the first iteration, mid is calculated as 5. We call the guess API with the value 5, and it returns 1, meaning the guess number is too low. This tells us the target must be in the upper half of the range, so we update left to mid plus 1, which becomes 6. In the second iteration, we recalculate mid as 6. This time, calling guess 6 returns 0, indicating that we have found the target number. The algorithm then terminates and returns 6 as the output. After finding the correct number in the first example, we now move to another scenario where the target is 1, and the input range is again from 1 to 10. We begin with the same initialization, left is set to 1 and right to 10. In the first iteration, we calculate mid as 5. When we call guess 5, it returns -1, meaning the guess number is too high. This indicates that the target must be in the lower half, so we update right to mid 1, which becomes 4. For the second iteration, we calculate a new mid value as 2. Calling guess 2 also returns -1, meaning the guess is still too high. Again, we narrow the range by updating right to mid 1, which now becomes 1. Finally, in the third iteration, mid is recalculated as 1. This time, guess 1 returns 0, indicating we have found the target. The algorithm terminates and outputs 1 as the result. Now, let's examine the third example, where the target number is at the upper boundary, 10. As before, we initialize left at 1 and right at 10. In the first iteration, we calculate mid as 5. Calling guess 5 returns 1, meaning the guess is too low, so we move the left pointer up to mid plus 1, which becomes 6. In the second iteration, the new mid value is calculated as 8. Calling guess 8 also returns 1, indicating it's still too low, so we update left to mid plus 1, which becomes 9. In the third iteration, mid is recalculated as 9. Once again, calling guess 9 returns 1, so we shift left to mid plus 1, setting it to 10. At this point, the range has been reduced to a single number. With left now equal to 10, we proceed to the fourth iteration. Here, the mid is calculated as 10. Calling guess 10 returns 0, confirming that the guessed number matches the target. The algorithm terminates and returns 10 as the final result. Through this example, we can see how binary search efficiently narrows the range by having it at each step. This approach ensures a time complexity of O log n, as the number of iterations is proportional to the logarithm of the input size. Additionally, the algorithm gracefully handles edge cases, such as when the target is at the boundary values of the range, like 1 or 10. This demonstrates both the correctness and efficiency of the solution. The time complexity of this solution is determined by the binary search approach it employs. With each iteration, the algorithm splits the search range in half, dividing the interval, left, right, into two equal parts. It calculates the midpoint, calls the guess API, and adjusts the range based on whether the guess is too high, too low, or correct. This halving of the range continues until only one number remains. For an input size of n, the number of times the range can be halved corresponds to log base 2 of n, or log_2, n. As a result, the overall time complexity of the algorithm is O log n. The key operations, calculating the midpoint, calling the guess API, and adjusting the range, are all performed in constant time, O1, during each iteration. Since there are O log n iterations, the total time complexity remains O log n. The overall time complexity of the solution is O log n, as derived from the binary search process. For space complexity, the algorithm is highly efficient. It only uses a few variables, left, right, and mid, to track the search range, all of which require constant space, or O1. Additionally, the guess API does not use any extra memory, and the algorithm avoids recursion or auxiliary data structures. Therefore, the space complexity is O1. Now, let's consider the best, average, and worst cases. In the best case, the correct number is guessed on the first attempt, which happens when the target is the initial midpoint. This takes constant time, O1. In the average case, the algorithm performs binary search until the range reduces to one number, requiring approximately log_2, n, iterations, so the time complexity is O log n. Similarly, in the worst case, the range is halved repeatedly until only one number remains, and this also demands O log n iterations. Hence, the time complexity is O log n across all scenarios, with O1 space usage. When comparing this binary search approach to a naive solution, the advantages become clear. A naive method would check each number sequentially from 1 to n, calling the guess API for every number until the correct one is found. In the worst case, this approach would require n iterations if the target number is at the end of the range, leading to a time complexity of O(n). However, the space complexity for the naive approach remains O(1), as no additional memory is needed. In contrast, the binary search approach reduces the time complexity to O log n by having the search range with each iteration, while maintaining the same minimal space complexity of O(1). This makes the binary search approach significantly more efficient, especially for large values of n, where the difference between O(n) and O log n becomes substantial. To mathematically prove the O log n time complexity, consider how the binary search reduces the range of numbers. Initially, the range is n. After one iteration, the range is halved to n/2. After two iterations, it is n/4, and after k iterations, the range becomes n/2 to the power of k. The process stops when the range reduces to 1, which gives the equation n/2 to the power of k equals 1. Solving for k, we find that k equals log_2, n. This means the algorithm performs log_2, n, iterations in total. Since each iteration involves constant time operations, calculating the midpoint, making a single API call, and adjusting the range, the overall time complexity is O log n, as derived. This mathematical reasoning confirms the efficiency of the binary search approach. When tackling algorithmic problems, there are some common pitfalls you should avoid. First, not leveraging the constraints of the problem can lead to inefficient solutions. For instance, if you're given a sorted array, it's a clear indication that you should use binary search instead of a linear search to achieve better performance. Ignoring these hints can often cost you valuable time and efficiency. Second, it's crucial to account for edge cases. For example, don't assume that the input size will always be manageable. Scenarios like an empty array, a single element, or maximum constraints, such as n being as large as 10 to the power of 6, can easily cause runtime errors or time limit exceeded issues. Testing for these edge cases is essential. Another mistake is overcomplicating your solution. Adding unnecessary logic or overly complex data structures not only increases the chances of bugs but also makes your code harder to debug and maintain. Finally, while optimizing time complexity, don't forget about space complexity. Recursive solutions, for example, can cause stack overflow errors in some languages unless tail call optimization is applied. Always aim for a balanced approach between time and space efficiency. Another common mistake is failing to clarify the problem requirements before diving into coding. Misunderstanding the constraints or edge cases can result in a solution that doesn't fully address the problem. Always take the time to confirm these details, especially in an interview setting. Speaking of interviews, there are a few key insights to keep in mind. Recognizing common algorithmic patterns like binary search, sliding windows, or dynamic programming can save you significant time. These patterns often recur in different variations, so practicing them is invaluable. Clear communication is equally important. Explaining your thought process while coding not only demonstrates structured thinking but also gives the interviewer an opportunity to guide you if needed. Additionally, discussing trade-offs between time complexity and space complexity shows a deeper understanding of the problem. Finally, always test your solution before submitting it. Walking through your code with test cases, particularly edge cases, helps catch errors early and ensures that your solution is robust. To strengthen your understanding of the binary search pattern, it's helpful to explore related problems. For example, LeetCode 704 focuses on implementing a simple binary search on a sorted array. This is a great place to practice the fundamentals. Another related problem is LeetCode 278, first bad version, where you use binary search to efficiently locate the first bad version in a sequence. If you want to go a step further, LeetCode 74, search a 2D matrix, applies binary search in a slightly more complex scenario, treating a 2D matrix as if it were a flattened sorted array. Finally, the problem we're discussing, LeetCode 374, guess number higher or lower, demonstrates how binary search can be adapted to work with an external API like guess. These problems collectively offer a well-rounded way to practice and deepen your understanding of how and where binary search can be applied. Now, let's consider some alternative approaches to solving problems and the trade-offs they involve. Linear search is a straightforward method that's quick and easy to implement. However, it becomes inefficient for larger input sizes due to its O(n) time complexity. Binary search, on the other hand, is highly efficient with O(log(n) time complexity, but it requires the input to be sorted and needs careful handling of midpoint calculations to avoid overflow in some implementations. Hashing is another approach that provides O(1) average time complexity for lookups, making it extremely fast, but it comes at the cost of additional space usage and isn't suitable for scenarios requiring sorted traversal. Lastly, divide and conquer strategies can be powerful as they reduce the problem size exponentially. However, they often involve the overhead of recursive calls and may require merging logic in certain cases, which can add complexity. Choosing the right approach depends on the specific problem constraints and the trade-offs you're willing to make. Great job making it through. To wrap up, we reviewed the key algorithms and takeaways from solving problem number 374, guess number higher or lower. We highlighted the importance of understanding APIs, optimizing search techniques, and choosing the right approach for efficiency. Thanks for watching, and we hope to see you again for another coding challenge. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!